A colossal impact scar, nearly 4 billion years old, lies hidden beneath the Moon's south pole. And within it are materials that could one day alter global power dynamics. NASA has now confirmed something remarkable. The South Pole, Aitken Basin, is not only the largest known impact structure on the Moon, it is also a preserved geological archive. The impact punched through the lunar crust and hauled up primordial material from depths that were never meant to be exposed. What scientists discovered there changes the conversation entirely. Researchers have identified thorium-rich regions, dense iron concentrations, and rare earth elements embedded in ancient ejecta. Crucially, the planned Artemis 3 landing zones sit directly atop this 4-billion-year-old deposit. This is no longer just about collecting moon rocks for science. These materials could be worth, by some estimates, up to $1 quadrillion. And every spacefaring nation is well aware of that fact. The South Pole, Aitken impact, formed during the Moon's earliest epoch, when it was still cooling from a global magma ocean. The collision was extreme, more energetic than any other basin-forming event in lunar history, excavating deeper than anything else we have observed. New modeling shows the impactor arrived from the south, and that detail matters. It explains why the deepest material was deposited where it is today. The ejecta blanket spread predominantly to the southwest, carrying with it fragments of the Moon's lower crust and even portions of the upper mantle. The significance of this becomes clear when you consider how the Moon formed. As the lunar magma ocean crystallized, the last remaining liquid concentrated elements that do not fit easily into solid minerals, potassium, rare earth elements, and phosphorus, were enriched in these residual melts, known to scientists as KREP material. The South Pole, Aitken impact, struck before this differentiation process fully finished, excavating these chemically rich remnants and scattering them across the surface as ejecta. That ejecta is now accessible without the need for deep drilling. Surface collection alone could reach it. The Artemis 3 sites were placed directly on top of this ancient deposit. Intentionally, officially, it is framed as scientific exploration. And the geology is indeed extraordinary, but the strategic implications are immense. Thorium is a key ingredient for advanced nuclear power concepts. Rare earth elements are essential for modern electronics, renewable energy systems, and military technologies. These are not just interesting samples for laboratories. They are the same materials that underpin geopolitical competition on Earth, now confirmed to exist on the Moon in concentrated and reachable form. Orbital data revealed another surprise. NASA's Grail mission mapped the Moon's gravity field with unprecedented resolution and detected long, linear gravity anomalies stretching as far as 500 kilometers. These features have no visible expression at the surface. That absence is telling. It means they are older than the heavily cratered terrain we see today. They predate nearly everything visible on the Moon's face, making them among its most ancient structures. They are not lava tubes. They are too large, too deep, and too structurally distinct. Instead, scientists believe they are massive subsurface voids or density variations created by stresses from the South Pole, Aitken impact billions of years ago. If humans can access these structures, they would offer natural radiation shielding far superior to anything that could be built on the surface. They would effectively provide ready-made infrastructure for permanent habitation, requiring little more than access points and life support systems. This matters because radiation is arguably the greatest barrier to long-term human presence on the Moon. Unlike Earth, the Moon has no global magnetic field and no thick atmosphere. Any surface habitat is exposed to constant and severe radiation hazards. One threat comes from solar particle events, sudden bursts of high-energy protons and heavier ions released during solar flares and coronal mass ejections. These events are unpredictable, and a single one can deliver a lethal dose of radiation within hours if proper shielding is not in place. The second threat is continuous and unavoidable galactic cosmic rays. These particles originate far beyond our solar system, often from supernova explosions, and they penetrate nearly all conventional spacecraft and surface habitats. Long-term exposure significantly increases cancer risk, damages the nervous system, and causes degenerative tissue effects. Because of this, any sustainable lunar base must be designed around radiation protection. Surface habitats require meters of shielding, often by burying structures under thick layers of regolith, or by deploying complex active systems such as artificial magnetic fields, which demand enormous power and technological sophistication. Subsurface voids change everything. Underground, radiation levels drop dramatically. Temperatures remain stable. Micrometeoroid impacts are no longer a constant danger. Nearly every requirement for a permanent settlement is already met beneath the surface. NASA would not need to construct massive protective structures from scratch. They would only need to locate access points and move in. That shift fundamentally alters the economics of lunar colonization. Water ice is the final piece that makes all of this possible. Confirmation of substantial ice deposits instantly transformed lunar strategy. The Cross mission showed that permanently shadowed craters like Cabeus contain water ice at roughly 5.6% by mass within the regolith. That is not a trace amount, is a workable resource. Analysis of the impact plume revealed additional volatiles as well: light hydrocarbons, carbon dioxide, sulfur compounds, and metals such as mercury, magnesium, calcium, and silver. Each one expands what can be produced locally through in-situ resource utilization. Water can be split into hydrogen and oxygen to create high-performance rocket propellant. It supports life through drinking water, breathable oxygen, and agriculture. It becomes the foundation for sustained activity beyond Earth orbit. Permanently shadowed regions act as cold traps, with temperatures dropping below -330 degrees Fahrenheit. Volatiles delivered by comets or produced through solar-wind interactions freeze and remain preserved for billions of years. The Moon's south pole geometry, with its deep craters and constant shadows, concentrates these resources in one place. Yet there is a serious engineering challenge that is rarely discussed. The same conditions that preserve water ice make landings extremely risky. Regolith in permanently shadowed regions is highly porous, with void spaces reaching up to 70% down to several meters. It has never been compacted by thermal cycling or disturbed by temperature changes. It behaves more like cosmic powder than soil. Landing a heavy spacecraft on such terrain risks catastrophic bearing failure, where the lander could sink or punch through meters of unconsolidated material. This hidden danger is one of the most difficult obstacles facing lunar operations at the South Pole, even as the region offers the greatest rewards. Mission failure, loss of crew, and a complete strategic collapse are very real possibilities. The Moon may be rich in resources, but its surface cannot safely support sustained operations without advanced geotechnical solutions. Nowhere does this contradiction appear more clearly than at Shackleton Crater. Shackleton Crater captures the South Pole paradox in its purest form. It spans roughly 21 kilometers in diameter and plunges about 4.2 kilometers deep. Its rim receives near-continuous sunlight, making it ideal for power generation, while its interior floor remains permanently shadowed, preserving volatile compounds for billions of years. On paper, it looks like the perfect location for a permanent lunar outpost. The problem is access. The crater floor lies nearly 2.6 miles below the rim, demanding specialized mobility systems. And the regolith down there is likely just as porous and unstable as that found in Cabeus Crater. This is where ground-penetrating radar becomes indispensable. GPR works by sending radio wave pulses into the ground and measuring how they reflect off subsurface boundaries. Differences between rock and ice, or solid material and voids, change the strength and timing of the return signal. From this data, scientists can reconstruct the depth, layering, and geometry of buried structures. NASA's Viper mission carries advanced ground-penetrating radar specifically designed to map volatile deposits and characterize regolith layering at the lunar South Pole. This effort goes far beyond locating resources. It is about certifying the ground itself. NASA must determine where landers can safely touch down, where rovers can reliably travel, and where drilling operations can proceed without triggering subsurface collapse. China's Chang'e 7 mission includes similar radar systems, reflecting the same understanding. The nation that first maps safe landing zones alongside high-value volatile concentrations gains a decisive advantage in establishing a lasting presence on the Moon. This raises a fundamental question. What truly drives a competition? scientific discovery, or control over resources? That question becomes unavoidable when considering the scale of what is at stake. Speculative valuations place the total worth of lunar resources at more than $1 quadrillion. That estimate includes helium-3 for future fusion energy, rare earth elements critical to modern industry, metals for space-based manufacturing, and water ice for propellant production. At that scale, the moon ceases to be merely a scientific destination and becomes a strategic asset. Such valuations inevitably provoke geopolitical rivalry. They encourage resource monopolization and raise the risk of militarizing cislunar space. India's Chandrayaan-3 landing near the lunar South Pole underscored the urgency of this moment. Analysts quickly declared that the race for lunar resource development had effectively begun. That assessment was not exaggerated rhetoric. It was a sober strategic conclusion. Security analysts have repeatedly warned that allowing deep space leadership to concentrate in the hands of non-democratic regimes could undermine global stability and the ability to protect shared interests. The psychological, political, economic, and scientific gains achieved during the Apollo era are now being contested by ideological and economic rivals. As civilian, commercial, and military space capabilities increasingly overlap, the challenge intensifies. Protecting strategic lunar assets or denying access to potential adversaries requires counter-space capabilities, raising the likelihood of conflict extending beyond Earth orbit into the cislunar domain. The confirmation of vast lunar wealth only heightens the need for stable and widely accepted governance frameworks. Without international agreement on resource rights and extraction norms, competition risks escalating toward confrontation. This is the ethical and strategic dilemma NASA must navigate. The Artemis program operates under a mandate to benefit all of humanity. Yet that principle becomes difficult to apply when resources worth trillions are extracted by a small number of nations and corporations. NASA's policy documents openly acknowledge this tension. They emphasize inclusive and reflective public engagement, participatory technology assessments, and early discussions of ethical, legal, and societal implications before large-scale extraction begins. This approach is not merely symbolic. It is intended to reduce strategic risk. Policy analysts warned that the concentration of space resources could lead to what they describe as cosmic inequality. If access to critical locations and materials, such as the water ice at the lunar South Pole, is controlled by a select few, it undermines the foundational idea that space is a shared domain for all humankind. Such monopolization could deepen existing inequalities on Earth by funneling extraterrestrial wealth, technological capability, and strategic leverage into the hands of already powerful actors. The divide between spacefaring nations and those without such capabilities would widen dramatically. This scenario risks creating a new form of space colonialism, where the benefits of exploration and development are unevenly distributed, stalling global cooperation and long-term progress. International stability increasingly depends on establishing cooperative frameworks that ensure space resources are used responsibly and in ways that benefit the global community as a whole. Cultural and ethical considerations further complicate the issue. In many cultures, the moon holds deep spiritual or symbolic significance, and large-scale extraction may conflict with those beliefs. Environmental ethics also come into play, as irreversible damage to lunar landscapes raises questions about humanity's responsibility beyond Earth. Unchecked exploitation would represent a failure of stewardship on a cosmic scale, making proactive policy essential. NASA has responded by carefully shaping public messaging. Agency communications emphasize paradigm-shifting scientific discovery and frame resource utilization as a means to enable deeper exploration rather than simple exploitation. In situ resource utilization is presented as a necessity for sustainable presence, not a profit-driven mining operation. This strategy blends technical realism with inspirational goals. Mission summaries focus on expanding humanity's understanding of the solar system while inspiring future generations. Public engagement is encouraged through astronaut-borne cameras that document surface operations and through citizen science initiatives that invite people to participate directly in data analysis. Taken together, these efforts reveal what is truly unfolding, not just a return to the moon, but the opening chapter of a far more complex and consequential era of space exploration. NASA understands that confirming primordial metals and assigning trillion-dollar valuations will invite intense global scrutiny. They know rival nations will accuse them of attempting to monopolize resources. They also know ethical objections will arise from environmental groups and cultural advocates. To address this in advance, NASA is deliberately building moral credibility through public participation and transparent ethical discussion. That public involvement creates democratic legitimacy for any future extraction activities. It also distinguishes the American approach from more opaque, authoritarian models. The goal is to preserve cooperation while still competing. A carefully calculated geopolitical strategy presented outwardly as public engagement. Artemis 3 is officially aimed at scientific exploration of the lunar South Pole. Its core objectives include field geology, sample collection, and the deployment of scientific instruments. Yet the mission design clearly blends pure science with resource utilization through the establishment of the Artemis base camp and reliance on local materials. Now that an ancient, high-value resource base has been identified, scientific discovery naturally accelerates a shift from exploration to strategic use. That transition increases international tension regardless of how often peaceful intentions are emphasized. China's lunar program is pursuing similar goals. The Chang'e missions demonstrate rapid technological progress, including ground-penetrating radar, sample return capabilities, and planned polar operations. Each success reduces the gap between Chinese capabilities and long-standing American leadership. The strategic reality is unforgiving. The nation that establishes a permanent presence first gains a disproportionate advantage in resource access, operational experience, and infrastructure placement. Coming in second means dependence on competitors for materials that enable deep space expansion. That dependency closely resembles current terrestrial rare earth markets, where China dominates production and processing. Countries reliant on Chinese supply chains face strategic vulnerability during geopolitical crises. Recreating that same dependency in space would give China leverage over allied space programs and Earth-based industries that rely on lunar resources. The 4-billion-year-old secret uncovered at the Moon's South Pole is therefore not just about ancient geology. It is about future power projection, control over thorium, rare earth elements, and volatile compounds means control over the economics of space expansion. That influence extends back to Earth through supply chain dominance and industrial leverage. What Artemis 3 is poised to reveal will shape that future directly. Astronauts will land on the South Pole, Aitken ejecta field, conduct surface geology, collect samples from primordial deposits, and deploy instruments to study subsurface structure and volatile distribution. Those samples will either confirm that crust-rich materials are economically viable or show concentrations too low for profitable extraction. Subsurface measurements will determine whether the ground can support heavy landers or if extreme porosity demands entirely new landing strategies. Either result reshapes the next decade of lunar competition. High-grade confirmation would trigger rapid development by every space-capable nation. Lower than expected concentrations would shift focus to other regions or delay timelines. But even in that case, the core geological mechanism would still be proven. The South Pole, Aitken Impact excavated deep lunar material containing elevated thorium and rare earth elements. The resource undeniably exists. The remaining questions concern concentration, accessibility, and extraction cost. That alone is enough to sustain competition. Unlike on Earth, where low-grade deposits are often abandoned, lunar resources face no local competition. Any concentration of strategically important material can justify development if it reduces dependence on terrestrial supply chains. NASA's public messaging is therefore not about softening disappointment if resources prove limited. It is about managing global reaction if they prove abundant. It is about setting ethical frameworks before extraction begins and framing American-led development as responsible stewardship rather than exploitation. The urgency behind all this is clear. NASA emphasizes technical resilience and goal-driven planning, ensuring that long-term objectives remain stable despite budget pressures or technical setbacks. This approach, often described as designing from the desired outcome backward, keeps efforts aligned with the intended end state. That end state is not simply scientific knowledge. It is guaranteed access to strategic resources that support sustained deep space presence, continued leadership in cislunar development, and prevention of adversary monopolization over materials that shape both space-based and Earth-based industries. The 4-billion-year-old impact provides the geological justification. The trillion-dollar valuation supplies the economic motivation. International rivalry creates urgency, and public engagement supplies political legitimacy for what follows. Once Artemis 3 confirms those primordial deposits, the moon ceases to be just a destination. It becomes contested territory. Resource extraction shifts from possibility to geopolitical necessity. Any nation that hesitates risks losing an advantage it may never regain. The ancient impact that formed the South Pole, Aitken Basin unearthed materials that waited in frozen isolation for billions of years. Now multiple nations are racing to secure them. The outcome will shape the next century of space development. Winners define supply chains and independence. Losers accept reliance on competitor-controlled resources. That is the deeper reality NASA is preparing the public to confront. Not that the moon contains resources, that was always expected, but that those resources are valuable enough to spark competition resembling historical conflicts over Earth's most critical materials. The moon, scarred by ancient impacts, volcanic flows, and immense age, has unexpectedly become humanity's next geopolitical flashpoint. This is no longer an abstract scientific pursuit or distant curiosity. The drive to extract lunar resources, establish permanent bases, and control key orbital and surface locations has placed our once silent neighbor at the center of an accelerating global struggle. The public preparation unfolding now is not mainly about managing excitement over discovery. That is the accessible narrative. Beneath it lies a far more deliberate objective, shaping global perception, securing investment, and laying the legal and diplomatic groundwork for asserting national and corporate claims over the moon's most valuable assets. The race is underway, not for symbolic achievement, but for strategic dominance in a new and unforgiving frontier. This moment marks the transition from cooperative exploration to contested resource development. How humanity responds will define the future of space. Whether the moon becomes a shared heritage or a battleground for extraction will determine the path forward, not just beyond Earth orbit, but for global stability itself.